Welcome back. In this video, we're going to start section 5.3 on the applications of double integrals. The goal of this section is to use double integrals to find the area of planar regions and to find the volume of solids bounded by functions of two variables. Area. Proposition 5.3.1. If D is a type 1 or a type 2 region in the plane, then the area of D is A of D is the double integral over D of 1 dA. Proof. We're going to do this in the case where D is type 1, but a very similar argument works when D is type 2. So if D is type 1, let's let A be less than or equal to X be less than or equal to B, and G1 of X be less than or equal to Y less than or equal to G2 of X. And before we go any further in the proof, let's just recall from calculus 2, from integral calculus. So the calculus of a function of a single variable. If you had a region D, which looked like, let's give ourselves some axes here. If you had a region D that was bounded above by G2 of X and below by G1 of X, from X equals A to X equals B, then the area of that region you would have calculated as the integral from A to B of the top function, so G2 of X, minus the bottom function, so G1 of X dx. So that was how you would have done this with a single integral, a variable, a function of a single variable. So now let's look at the double integral variant. So going back to the proof here, the double integral over d of 1 dA, well, 1 is a continuous function, a constant function, so we can write this as the integral from a to b of the integral from g1 of x to g2 of x of 1 dy dx. And if we take an antiderivative of the inner integral, where we're anti-differentiating with respect to y, so that's the integral from a to b of y, and using the fundamental theorem, we're going to run that from g1 of x to g2 of x dx. So we're going to subtract the top minus the bottom, so the integral from a to b of g2 of x minus g1 of x dx, and what do you know? That's exactly the formula from your integral calculus course, which, so therefore, is the formula from the calculus of a function of a single variable. So, which is the formula from the calculus of a function of a single variable for the area of D. That's the formula that you used in integral calculus. Another way of thinking about this is geometrically. So we have been looking at functions in R3, and so if we have a region D down in the plane, if this is our region D here, and if we have a function f of xy equal to 1, so if our function f of xy is equal to 1, well, that is a function that is floating above D, a function graph, a surface. So let's draw that floating above D back there. And if this is 1, then that is a flat surface. And I can sort of draw it's coming down with straight sides onto the region D. And so we know that the double integral over D, the double integral over D of f of xy dA, well, we know that one interpretation of that is volume. And so that's the double integral of D of 1 dA. That's the volume of the region. Now, volume, this is a prism of sorts. It has straight sides over a base and a top that match in shape. And so that is the area of the base times the height. That's what the volume is. Well, the volume, or the area of the base, is, well, it's the area of D. And the height, well, the height is that function value, which is height of 1. Right? That's the height of that prism. And so we get that the area of D is indeed the double integral of over D of 1 dA, even though its volume numerically, it's equivalent to area because you're multiplying the area by 1 to get the volume. So there's a geometric illustration of why this formula works. So whether you want to think of it algebraically with your Cal 2 formula, or whether you want to think of it geometrically, the integral of 1 over a region D dA gives us the area of that region D. In the next video, we'll do an example where we'll use this formula to calculate the area of a region.